Uh, Dear students, it's me Ashik Faiz, and I'm recording this demo lecture on a topic of class 12th alternating current, the root mean square value of an AC. We call it root mean square value of an AC. The square value of an AC or alternating current. So the first thing first, like what is an alternating current? Alternating current, by the definition, it means it's a kind of a current uh, whose value changes over time. Let's say this is time axis and this is the current axis. The in case of DC, what happens? The current is constant over the time. At time t equals to 0 or time t equals to 2, time t equals to 3. At every point of time, the current is same. But in an AC circuit, what happens? The current periodically changes its value and direction also. So this is positive and this is negative. This means positive and negative means the current is changing the direction. The first time it's flowing in one direction, and the second time interval it is flowing in the other direction. At the same time, the value of current, you can see that the value of current is also fluctuating with respect to time, and this is the maximum value of current, and I denote that with I naught. And you can see that this graph is an example of a sine graph. So I can say that the current at any time can be denoted by an equation I naught sine omega t, where this omega is 2 pi by t. Okay, so the value of the current changes with respect to time. So I have to basically determine the root mean square value of an alternating current. I will find out RMS. So basically, what is RMS? So RMS, let's say we have got two circuits. The first circuit is an AC circuit. Okay, the first circuit is an AC circuit, and if there is a certain current and the heating produced, there will be a certain heating produced, which will be equals to I square RT. Okay, and there's another circuit, but with a DC source here. So we have an AC source over here, and we have a DC source over here. So it will also produce a heating effect. It will also produce a heating effect because this and this heating because the current over here is constant, so it will produce the amount of heat. Let's say this will be equals to I square RT, and I denote this I square RT as IRMS. So the amount of heating produced over here and the amount of heating produced over here will be equal over a certain time interval, over a constant time interval. So this amount of current, when it is flowing in an AC circuit, we call that the RMS value. So this RMS value, this RMS is how much times of the peak value I have to find out, this x. So this x will determine the value of the RMS. So now let's try to calculate it. So I'm erasing it for now to further solve it. Okay. Okay. Let's say the heating produced, let's say that the heating produced is equals to I square RT. This is the Joule's law of heating. So in an AC circuit, let's say in an AC circuit, okay, in an AC circuit. So let's say for a small time interval, the heating produced will be dH will be equals to I square R, and since it is heated for a small time, dt. Now integrating over a limit, let's say that I have to find out the amount of heating produced from 0 to t, where t is the time interval. So I write 0 to t into dH will be equals to I square R into dt over the interval 0 to t. So in this 0 to t, how much time is how much current is produced? This I, which is equals to, in an AC circuit, I is equals to I naught sine omega t, as I already explained you in the previous slide. Now here, so over the time 0 t interval, let's say the heating produces H, which is equals to I can write it's I naught sine omega t, so it will be I naught square sine square omega t into dt and integrating it over the limit 0 to t. Next, I integrate it. So sine omega t is a trigonometric value that cannot be integrated directly. So I convert it into another identity. H is equals to 0 to t I naught square. Sine square to light is 1 minus cos 2 omega t upon 2. Okay, into dt. Now, forget this r here. Now, solving it further, we get it h is equals to taking this I naught is a constant value, r is also a constant value. R is distance, I naught is the maximum value of the current. So I naught square and r, and this 2 I take it out of the integration. So it is I naught square r upon 2 into 1 minus cos 2 omega t into dt. Alright, now this h is equals to naught square r upon 2 and integrating it over the limit 0 to t. So 1 will become what? T and cos omega. Okay, now it will be what? 1 minus sine omega t and 0 to t. That will be the limit. Here it is 0 to t. Okay, now further calculating, it will be I naught square r upon 2 into 1. If you put at the upper limit, it will be t and omega. So we know that omega is 2 pi upon t. If we put 2 pi, 2, here it is 2 into 2 pi, it's 4 pi. So 4 pi, the sign at places of 2 pi, 0, 2 pi, 4 pi. At these places, the value of the sign is 0. So it will be 0, the upper limit, minus, if you minus, the lower limit will be 0. 0 minus sine 0 is also 0. So the final value of heating that is calculated turns out to be I naught square r upon 2 into t. So that's the final value of heating produced. And since this h is equals to I square rt in a DC circuit, so I considered in a DC circuit this I as I RMS. So if I put these compare this equation 1 with the final equations, we say that I R ms square r into t, which is equals to I naught square r into t upon 2. RT got cancelled, this is square got cancelled, and there's a root over here. So finally I RMS turns out to be I naught upon root 2. So I RMS is equals to 0.707 into I naught. So the value of the IRMS will be 0.707 times the maximum value of the peak current in an AC circuit. I hope you guys understood the concept of the RMS and the way I have derived the multiplication factor with the peak value of current to determine the root mean square value of the current. Thank you.